So today we're going to be using Raoult's law to solve for the bubble, well not to solve, but to determine some equations for bubble pressure, bubble temperature, dew pressure, dew temperature. And it'll let us solve for the individual components of a mixture with n component or n substances. So Raoult's law is pretty simple. It states that the liquid component of substance I times the saturation vapor pressure of component I is going to be equal to the vapor component, and these are mole fractions. The vapor component times the total pressure, and then from there, it's pretty obvious that that's going to be equal to the partial pressure. So we have this scenario wherein we are exerting a pressure on a closed system with n components, and they're all liquid, and we want to know at what pressure will the first vapor bubble form. And we don't know the pressure, but we do know the temperature. So this time we're going to be solving for bubble pressure. So let's write out all our equations in terms of n components, and it'll make it a bit easier to solve it in terms of summations. So if we look at this, we can say, we'll start off with P1 plus P2 plus Pn is going to be equal to the total pressure. So basically the sum of the partial pressures is going to be equal to the total pressure. Well, we know from Raoult's law that can also be expressed as the vapor phase component of 1 times the total pressure plus the vapor phase component of 2 times the total pressure all the way through component n is going to be equal to the total pressure. And once again, we can rewrite this in terms of the liquid phase. It's going to be equal to the total pressure. So if we take a look at this again, this equation right here can be expressed as the pressure is going to be equal to each individual component's liquid phase times the saturation vapor pressure from the first component all the way through n components. So that's our first big equation. The second thing we want to look for is we want to be able to express this in a way that isolates the vapor component. So we want to solve for yi or yn or whatever it may be. So if we rewrite this for only one component, we have yn P is going to be equal to the partial pressure of substance N. It's pretty simple to solve for that. We know that Yn is going to be equal to the partial pressure of N divided by the total pressure. Now we have our equation up here, and you can't see it. I don't want to scroll up because I'm going to lose my blank space if I do that. But looking at the equation in terms of yn and expressing it similarly to this, we can say that yn is going to be equal to the partial pressure of n is going to be equal to the total pressure. And I'm going to leave out some of the fancy math stuff just for the sake of time. So again, rewriting this, you can say that yn is going to be equal to the liquid phase. Going back to Raoult's law, you can say it's equal to the liquid phase times the, I'll try that again. The liquid phase times the saturation vapor pressure of that substance divided by, and then plugging in our equation for pressure. So that is how we can solve for the vapor pressure. So we have these two equations, and this, or not the vapor pressure, sorry, the bubble pressure. But now we need to look at a scenario that's similar, but this time we know the pressure that we're at, and the pressure is constant, but we don't know the temperature that we need to be at, if we need to add or remove heat. So in this case, we can rewrite the thing again. We can rewrite our equations. And now we need to solve for the saturation vapor pressure. So once again, we can rewrite this as x1 P1 saturation vapor pressure plus x2 yada yada all the way through xn is going to be equal to the total pressure. And now we know that we don't know our saturation vapor pressures. So once again, we can solve for these because we know Antoine's equation, log base 10 is going to be equal to each of these, the parameters an, bn, actually that's a minus, going by cn plus t, and we can write this for each component. And each component, the temperature is going to be the same. So we're going to end up with a system of equations, and we'll use a root solver in Python to actually solve for that temperature for all of our equations for n components. I believe we're only doing this with 2 components, but this could be applied to many, many more components. And using something like Python means that we can do it quickly, whereas by hand it would take ages or be borderline impossible. Whereas with the bubble pressure, it's a pretty simple equation. So we could actually do this with a calculator because we know the liquid components and we know the saturation vapor pressures of each of our components because we know the temperature. So all we'd have to do is sum these up in a calculator and divide. So now we can look at the due temperature and pressure. And actually, I'll go ahead and mark that. So in this case, we're going to have a similar scenario, but instead of having all liquid, we're going to have all vapor with n components. And we're going to be applying pressure. And we'll start off not knowing the temperature. Well, hold on. So if we have a PT curve here, pressure, temperature, and it'll look something like this. This is vapor, liquid, and then solid. And we know either the temperature or the pressure. We'll start off with temperature. We know the temperature that we're at, and we need to solve for the pressure at which the first drop of liquid will form. Because last time we were going from liquid to vapor, we want to find when the first bubble of vapor forms. This time we're going from vapor to liquid, and we want to find when the first drop of liquid forms. And so in one scenario, we'll know the temperature. In the other scenario, we'll know the pressure. So the due pressure is actually extremely simple, in my opinion. We'll start off with the fairly obvious equation that the sum of the mole fraction of the liquid phases is going to be equal to 1. And again, that seems fairly obvious, but you'll see how we're able to solve for the pressure from there. So from here, we know that x1, p1 sat, and actually I'll make those ends, is going to be equal to y2 times p. Or, sorry, not y2, yn. And our goal is to solve for this pressure. Well, we know that x of the n, or xn, is going to be equal to yn times p divided by the saturation vapor pressure of n. And from there, plugging that into this equation, we can say that the sum of xn is going to be equal to the sum of y, and that was a really bad summation, yn times p over the saturation vapor pressures. And once again, we know the saturation vapor pressures because we know the temperature in this scenario. We know, or we don't know P, but we do know our temperature. So from here, we can also say that this is going to be equal to 1, going back to this fairly obvious equation. So to solve for P, our total pressure, all we need to do is, actually I'll do this over here because I have a bit of blank space. And this is going to be our final equation. P is going to be equal to 1 over the sum of our yn over the saturation vapor pressures. And this is our due pressure. So looking at the due temperature, it's very similar to the bubble temperature. Looking at this equation right here, the pressure equals 1 over the sum of yn over Pn saturation. And I didn't really mention this with the bubble temperature. But again, we're going to come up with a system of equations because this can be expressed as Antoine's equation and we're going to be using a root solver in Python, and the root solver tries to get the equations that you supply it as close to 0 as possible through a series of guesses and some math I don't quite understand. So basically we're going to be saying 0 is going to be equal to 1 over our sum of yn over Pn saturation minus our pressure. And this is what we're going to be putting into Python. And we can do the same thing with our bubble pressure, or our bubble temperature, I should say. And if I'm just going to scroll back up and copy it. Oh wait, I can actually scroll instead of snaking my way up. Where did I put it? So we can take this equation here. Didn't mean to erase that, but that's fine. Copy and paste. Okay, well, you know what? Do we really need it up here? Let's move everything to the same place. It's moving rather slow, but we'll get there. We can do the same thing where we say our sum of our individual components in the liquid phase times the saturation vapor pressure minus P is going to be equal to 0, and that's our bubble temperature. So from here, all we need to do is put these into Python and use the root solver, and we'll be able to solve for bubble pressure, bubble temperature, dew pressure, dew temperature, either through some simple equations or through a root solver.